Okay, so hello everyone. Today I want to talk about IOAM Direct Exporting, especially how we implemented it inside the Linux kernel, along with support for some very well-known user space tools. First, since we are going to talk about IOAM, I will provide you with a short introduction on IOAM. Then, we will look into the details of direct exporting. Afterwards, I will explain how we implemented it in both user and kernel spaces. And finally, I will show you some measurements of the performance of the implementation. Okay, so we will get started on IOAM. IOAM is an acronym which stands for In Situ Operation, Administration and Maintenance. It's a telemetry solution for the network packets. It's actually standardized by the IETF across many packets. Usually, when we'll talk about telemetry solution, you have two main categories. You have active telemetry on one side and passive telemetry on the other side. For active telemetry, you generate network packets that are dedicated for telemetry. On the other end, for passive telemetry, you rely on the existing data packets. For IOAM, we are kind of doing a mix of both approach because we rely on the existing packets, but at the same time, we need to modify them a bit to derive the telemetry information. So how does it work? You have your usual network header and your packet payload. And what we will do is that we will insert IOAM information in between. This information can be instructions on the operations to perform related to telemetry, and potentially it can be some telemetry data. IOAM is not intended to be used on the wide internet. It's more intended to be used in a dedicated domain, like an ISP or data center network. So for encapsulating IOAM in existing protocol, if we take, oh, can you see the mouse, by the way? Okay, perfect. So as I've just explained, we have the packet header, the IOAM information, and the packet payload. Regarding the header, IOAM is currently standardized to be encapsulated with either the network service header or IPv6. For this talk and the implementation, we only consider IPv6. We will not take a look at NSH. Unfortunately, as probably most of you know, the standard about IPv6 does not allow the modification of the headers on in-transit packets. So we need to make a distinction between inline approach and the encapsulation approach. Inline approach will be used when the packet source and packet destination are inside the domain. And for that, we will store the IOAM information as an IPv6 extension header between the IPv6 header and the packet payload. On the other end, if you are just an ISP and the packets are just traversing a network towards your customers, if you want to be RFC compliant, you cannot modify that header. So what we will do is that we will add an additional IPv6 header, and that header will contain the IOAM information as an extension header. So you will create an IPv6 in IPv6 tunnel across the network. IOAM was standardized to be used in many use cases, so it has many operation modes, and these operation modes are referred formally to as option types. Currently, five of them are standardized by the IETF. I will go through all of them quite quickly. We have the preallocated trace option type. This one is important because we will talk about it later in the talk. For this option type, what you will do is that the first node on the path will add the IPv6 extension header, and the subsequent nodes will add the telemetry information inside that preallocated space in the extension header. The incremental trace option type is kind of similar, but each node will increase the size of the extension header instead of having the first node set the length at the beginning. Proof of transit will be used to prove that a packet has followed a predetermined path along the network. Edge-to-edge is not very important, so I will just skip it. And direct exporting, we will take a look about that a bit later. As you can see on the right column, each option type has a value which is assigned by IANA to be able to distinguish them. So if we remember, we are going to use IPv6 to encapsulate IOAM. So we will have an IPv6 up-by-up option, followed by the header, the IOAM header, and that particular header will be the same for every option type. This particular header will be followed by an additional header, and that header will depend on the option type being used. So what telemetry data can we gather with IOM? We have the usual up limit, node ID, identifiers of the interfaces, timestamp, and QDEF. I think the one which is most unusual is what they are referring to as opaque state snapshot. This data is just arbitrary data which is configured on each node and will be processed along the network path. All these data fields, there are more of them than the ones listed here, are all standardized in RFC 9197. Now, we have a good overlook of the IOM, and we'll take a more specific look at direct exporting. So, IOM Direct Exporting is one of the operation mode of IOM, which is standardized in RFC 9326. I think the easiest approach to understand direct exporting is to take an example. Let's assume we have these 4 routers, which are in a network domain. When you are doing direct exporting, you can do 2 operations, but these 2 operations are not mutually exclusive. You can do both of them. First, you can collect the telemetry data and report it towards an external entity. Or, you can also use both of them. You will locally collect the data and process it locally. So if we take back the same very small network infrastructure, we have the packet header designated by H, the packet payload designated by P. The first node along the path, which will be the ingress node, but in IOM they call it the encapsulating node, will add the IPv6 extension header, the general IOM header, which is the same for every option type, and the direct exporting header, which will be dedicated to direct exporting. Finally, the packet payload, obviously. So once the headers are added by the first node, the packet will traverse the network and reach the middle node, which are called transit nodes. These nodes, they cannot modify the headers, they can just read the values inside of them. And finally, when we reach the end of the domain, we want to remove all the headers to prevent the leakage of potentially sensitive telemetry information. So if we take everything and we put everything together, we still have our IPv6 up-by-up option, the general IOM header, which is the same for every option type, and the header dedicated to direct exporting. If we take a look quite quickly on all the fields in the header dedicated to direct exporting. First, we have the namespace ID. Here we need to be very careful. It's not a Linux namespace. It's 2 totally different concepts. A IOM namespace is just to identify or isolate subparts of your network. Then we have the flags, which is an 8-bit integer. Unfortunately, it's not clear what the authors of the RFC intended to do with it, and none of them are currently standardized. Then we have 8 bits for extension flags. 2 of these are currently standardized, and they just indicate the presence of an optional 4-byte field at the end of the header. The most significant bit will indicate the presence of a flow ID inside the header, and it's just the usual flow ID that we are all used to in networking. Then the second most significant bit indicates the presence of the sequence number. It's just a counter of packets belonging to the same flow. Then we have the IOM trace type, and this 24-bit integer represents the IOM metrics that we saw earlier that will be considered during the telemetry process. Finally, we have some reserved bit at the end. Unfortunately, inside the RFC, they do not specify how to export the data, the method and the format for exporting, nor how to collect the data. So we decided to make our implementation in the kernel space as generic as possible. This is something that is really open to discussion. We can have a chat about it at the end. But what we decided to do was to generate a generic netlink multicast event every time a packet reaches the router under the condition that this packet has the direct exporting header. If you have any other idea, feel free to say so at the end, or we can have a chat about it. Additionally, when we are triggering the generic netlink event, we decided to provide, along with the kernel space implementation, a small piece of software written in Go, which will listen to these events and convert them to the IPFix format for the users to use the solution. Okay, so now that we know what is IOAM Direct Exporting, I will talk about the implementation. But first, as maybe some of you may know, IOAM is not new to the Linux kernel. The preallocated trace option type, which is the mode of operation in which the encapsulating node adds the header and the subsequent nodes add the data inside that header, was presented at this conference a few years ago and is available in the kernel since version 5.15. It was subsequently improved in 5.16 to support in-transit packets with the IPv6 in IPv6 tunnel. Finally, it was updated in 6.9 for using generic netlink events. For this presentation, we will focus on the implementation of direct exporting, which rely on the existing one for the preallocated trace option type, while ensuring backward compatibility. So, the implementation relies on lightweight tunnel. As you can see on the left-hand side, we have a diff between what is currently in the mainline kernel and what the patch is applying. We moved the structure representing the preallocated trace option type into a union with the new structure representing the direct exporting. We think this approach is appropriate and maybe the best one because we ensure backward compatibility while reducing memory footprints because we will never have both of them at the same time. And if you look, we have the new structure IOM over IPv6 lightweight DEX, which is on the right-hand side. And this structure is the packet structure that we saw earlier with the up-by-up option, some padding to have the proper alignment, the generic IOM header for every option type, and finally, the header dedicated to direct exporting. If you remember from a few slides ago, inside the header, we have extension flags, and one of them indicates the presence of an optional flow ID. So we needed a way to generate those IDs. Once again, this is really a question on which we can have a discussion because we are not sure about the approach on how to generate these IDs, but we just decided to copy what is being currently done for segment routing over IPv6 in the kernel. If you have any other solution, feel free to say so. So now that we have a way to generate these IDs, we need to be able to store them. And to do so, we simply decided to add a hash table to the structure representing the data for IOM, and this structure is used for every Linux namespace. Okay, onto the reporting of the IOM data with generic netlink. We decided to reuse the existing group, which is named IOM6 events, but we decided to add a few attributes. First, we added an attribute to be able to distinguish between the preallocated trace option type and the direct exporting. Then we added 3 attributes for the direct exporting namespace, the flow ID, and the sequence number. And finally, we have 1 attribute for every IOM data field that can be exported or collected. The benefits of doing so is that we only report what is necessary, so we save a bit of memory and processing time. And also, the decision on what to do with that telemetry data is left to the end users. Okay, so we have transit nodes along the path, which are all the nodes in between the encapsulation and decapsulation. And for the direct exporting to happen, first, the node needs to verify if IOM is enabled. We will see in a few slides how to enable it. Then it needs to check if the value for the namespace in the header is matching one of the values configured on the router. If these 2 conditions are met, we will gather the IOM data and report it with generic netlink towards the user space. Finally, onto the decapsulation. First, we need to report the data, as we just saw with the transit node. And finally, we need to remove the headers, but here we need to be extra careful depending on how we added these headers in the first place. If these headers were added to the existing IPv6 header, we just have reached the destination and the packet will follow the usual code path inside the kernel. However, if we have reached the end of the domain, but not the final destination, we need to remove all the headers to prevent the leakage of the potentially sensitive telemetry information. And finally, we forward the packet towards its final destination. So as I have said at the beginning, we provide a kernel space implementation, but also support in some user space tools. We have updated Wireshark so that it can properly decode the header dedicated to direct exporting. This modification is already available in the mainline tree of Wireshark, but a new release has not been made available yet. So if you want to benefit from it, you need to compile Wireshark from the sources. To configure the lightweight tunnel, we have updated IP route to configure the route with the command on the bottom of the screen, sorry. So you specify encapsulation with IOM over IPv6, which is named IOM6. You can specify a frequency of insertion, sorry. That means in how many packets the IOM will be used in total. You can specify the mode, so with the inline encapsulation or encapsulation with the IPv6 in IPv6 tunnel, or you can use the auto argument to let the kernel figure it out. And finally, we need to specify all the values that are in the direct exporting header. The first one being the namespace value, the trace type, which represents what IOM data will be considered, and finally, the values for the extension flags. As you can see, we do not take the flags as parameter because none are currently standardized. And finally, we provide the small IPFix exporter that I have introduced a few slides ago. Okay, so how to use IOM Direct Exporting in the kernel? First, you need to configure the namespace on the node with IP root. Then you need to enable IOM on the interface with sysctl. You also need to configure the ID of the node and the ID of the various interfaces with sysctl. And finally, you configure the lightweight tunnel with IP root and the command that we saw on the previous slide. Okay, so now we know how it was implemented. We will look at the performance. To measure the performance, we decided to build a testbed with 2 servers. On the left-hand side, we have a traffic generator. It's using the software named T-Rex, which was released by Cisco. It's open source. And on the other side, sorry, we have our device on the test, which is running the modified version of Linux. It was running 6.12 because it was the latest available when I did the measurements, but of course, new versions have been released since then. We decided to evaluate the 3 operations, so encapsulation, transit, and decapsulation independently. Regarding the configuration on the device on the test, we have tuned a bit the network interface card. For all the tuning that we did, you will see that on the last slide, we have a QR code linking back to a GitHub repository with all the scripts that we have used, so you can see exactly how we configure the servers. On the next slide, we will see the results of the performance. They are all averages based on a run of 300 seconds for every parameter. So, onto the performance of the encapsulation. The first test that we decided to run was to measure the impact of each data metric taken independently. As we can see, As we can see, the data fields have no impact at all. This is an expected result because if you remember the structure of the header, the size of the header does not depend on the data fields being used. And also, if you are reporting data with generic netlink, all the data fields have a size of either 4 bytes or 8 bytes. So reporting 4 bytes or 8 bytes has no impact. Then we decided to measure the impact of the various extension flags. It's hard to see on the slide, but starting from a 5% injection rate, we can see that using extension flag has a very small impact. This is expected because you need to compute the flow ID, to do a hash table lookup to check if that flow is already known, and if it's not the case, you need to insert it inside the hash table. Finally, we decided to measure the impact of using the inline mode or the encapsulating mode. As you can see, if we use the inline mode and the encapsulating mode while specifying the source of the tunnel, we have the same performance. However, if we use the encapsulation without specifying the source of the tunnel, we have worse performance because we have a few more operations inside the kernel space. Regarding the transit, so this is for every node between the beginning and the end of the domain, we reach the same conclusion regarding data fields, which is that data fields have no impact on the performance for the same reason that we are just reporting 4 bytes or 8 bytes with generic netlink. Finally, we did the same test regarding the extension flags. As we can see, in this time, there is no difference because for the transit, we are just reporting the data with generic netlink. And when you are using extension flags, you will report 0, 1, or 2 4-byte integers, so there is no difference in computation. As a general conclusion regarding the transit, if you quickly compare these two slides, we can see that the transit has better performance in general compared to the encapsulation because we are just reporting the data with generic netlink without manipulating the packet to add the headers. Finally, onto the decapsulation, we did the same two tests with the data field and the extension flags. We reached the same conclusions once again for the same reason, but we can also conclude that if we compare quite quickly, the decapsulation has worse performance because on top of reporting the telemetry data, you also need to remove the headers and manipulate a bit the packet. As a general conclusion, let's say, on the performance, we can say that extension flags have very small impact. Data fields taken independently have no impact at all. Encapsulation, if you don't specify the source of the tunnel, leads to worse performance. And finally, the transit has better performance because you have less operations to perform. So this is the QR code I was talking about. If you scan this QR code, you have access to the GitHub repository with all the patches and all the scripts for the evaluation. I think for us, the next step will be to maybe improve a bit our patch if we have any feedback today and submit it to the mailing list to see if it might be interest to the community. That's it for me. If you have any question or feedback, feel free to ask. Thank you.
Yeah, I have a question about using Netlink to send the events, I mean, in the data path. Have you considered alternatives like tracing or even using packet capture, like faking, just using a regular packet capture to...
Do you mean like something like TCP dump or something like that?
Yeah, using packet capture.
Yeah,
like faking a fake packet, like, just the header you want to intercept.
I assume that's something that we can also do, but then you will need to, you will also have the processing in user space, so
but
that
Netlink, you also have to process this.
Yeah, exactly. Right? We decided to use Netlink because it was already inside the kernel for IOM, so we decided to reuse as much as possible existing code, but there might be a better solution.
Yeah, I would have tried tracing, just tracing.
Tracing?
Which is very fast. So.
Okay, I will have a look at that. Thank you for the feedback.
So we have... I think that question ultimately also comes down to what is the expected rate of events that you're getting out there. I'm not sure I fully understood that part.
Well, if you look at here, we are talking about, with a low injection rate, we are talking about approximately 1 million packets per second.
But that's also the events that are actually going to user space?
Yeah. For every packet, we will generate one event.
Yeah, so that's a lot for Netlink, for sure.
Yeah, we
probably don't want to be doing that.
Yeah, we decided also to measure the performance using a single queue on a single CPU core to have a very stable comparison basis. But of course, if you are many flows across many queues, you will have some scaling on the performance.
I'm not sure Netlink can actually process 1 million events per second. You are probably dropping many of them.
Okay.
Just
Okay, yeah, I will need to make further check on that.
Actually, one trick you can use, we have used, is to create a queue on a worker thread, and you send the events on a worker thread. It's
Okay.
not in the data path, but
Okay, yeah.
pseudo control. But yeah, I agree, you will lose events, and if that's important, you may need to build a backup mechanism.
Okay.
Since we have time, I'll ask another question. Why did you use two different kernels on the sender and the receiver?
There is no particular reason.
Okay.
It was for the test device, we used 6.12 because it was the latest available when I did the measurements. And on the other side, we used 5.17 because the server was running that kernel. But it's just a traffic generator, so in my opinion, the kernel version on the traffic generator has no impact at all.
All right, thanks. Well, we can go for an early lunch. Thank you.
Thank you.